Okay, I want to just have a look at a few reasonably straightforward problems on the principle of conservation of energy, which says in a conservative system where conservative forces are involved and forces that don't remove energy from the system, that the total change in potential energy plus the total change in kinetic energy is zero. In other words, the total change in energy, mechanical energy, is zero. So gravity is one example of a conservative force, throwing something up in the air. Gravity doesn't remove force, or doesn't remove energy from the system. Friction is a non-conservative force. If I drag a sled across the ground, generates heat, generates sound. Forces or energy is being removed from the system and going elsewhere. So what we're saying here, if I take this table I've drawn out here, I've got masses, I've got initial heights, I've got initial speeds, final heights, and what I want to do is find the missing kind of cell in each row. So I've got essentially 4 problems here that I'm going to cover in this class. They all represent projectiles traveling vertically, so I could use my master equations to solve these, but I'm going to use the principle of conservation of energy. Another way to interpret the principle of conservation of energy, in fact the way I always think of it, is that in a conservative system my total energy, my total mechanical energy at any position, let's call it position 1, is equal to my total mechanical energy at any other position, let's call it position 2. So at any position the total energy is equal to the total energy at any other position. It doesn't change. And we said the total mechanical energy is found by adding the potential energy and the kinetic energy. So the potential energy at position 1 plus the kinetic energy at position 1 is equal to the potential energy at position 2 plus the kinetic energy at position 2. That's what we're dealing with. Okay? A couple of things to know. Remember, potential energy is defined as being mgh. So if the height is 0, well, that means the potential energy is 0. Kinetic energy is defined as a half mv squared. So if v is 0, well, then the kinetic energy is 0. Okay, kinetic energy is based on speed. Potential energy depends on height for questions of this type. Okay, so let's have a look at the first one. I'm noticing here in this first row that the height is 0. That's jumping out at me, which means in this case the potential energy at position 1 will be 0. So at position 1 all of its energy is kinetic. I'm also noticing that its final speed is 0, so that's at position 2. Its speed is 0, which means at position 2 all of its energy is potential. So we have this kind of kinetic energy at position 1 must be equal to the potential energy at position 2. So what we have is a transfer of all the energy from being kinetic energy into potential energy. Now if you try to visualize this, what are we talking about? We're talking about something traveling vertically, a projectile under gravity, launched vertically upwards, an initial height of 0, that's from ground level, and traveling upwards until its velocity is 0 or its speed is 0. That means it's at its maximum height. So actually this final height will be the maximum height reached. Its kinetic energy at position 1 is defined as being a half times its mass, in this case that's 10, times its speed, 35 squared. And that's going to equal to its potential energy at position 2, which is defined by its mass, which is given as 10, times g, times its height at position 2, which is what we're looking at. Okay, notice the 10s here will cancel, and that's always going to happen with questions of this type. The masses will cancel. So we're going to get the height of this object is just going to be 35 squared over 2g, dividing by g on both sides. 35 squared over 2g. 35 squared is 1225. 2g, if I take g to be 9.8, that's about 19.6. And I'm going to use my calculator to do that. 1225 divided by 19.6, and that works out quite nicely at 62.5. These are in meters per second, meters per second. These are in meters. Okay, so my heights must be in meters, I suppose. I should have written that in. So 62.5 is my final height in this case. Okay, so there's the first row. Using the principle of conservation of energy, very important principle in physics. So let's look at the second row here. I look at the second row. Again, it's launched from an initial height of 0, so its potential energy in position 1 is 0. So at position 1, all of its energy is kinetic. At position 2, well, its final height is 16.1, so it will have potential energy. We don't know about its velocity, so we kind of assume it has kinetic energy as well. Okay, we might find out that it doesn't, but that will reveal itself to us if that's the case. The kinetic energy in position 1, well, that's a half times m is just given in this case as m times v squared. Well, its initial velocity here, that's 21 squared, and that's equal to its potential energy at position 2, which is mg, multiplied by its height, which is 16.1, plus its kinetic energy at position 2, which is a half times m, times its final velocity. That's what we're trying to find in here, this final velocity v squared. Okay, note the m's will all cancel. So the mass, actually this is not dependent on mass. The masses will all cancel all the way across. That's always going to be the way. I'm trying to find v. Before I find v, I'm going to find v squared. One thing I might do is double everything, so doubling a half to get rid of these fractions. That's going to be just the square of 21, which I think is 441. Here I'm going to get 32.2 times g, and then plus v squared. So I can establish that v squared will be 441. Subtract 32.2 g, which means that v will be equal to the square root of whatever that stuff is. Okay, so I'm going to use my calculator again here. 441. I'm going to let 9.8 be g, so 441 minus 32.2 times 9.8. That's 125.44. I'm going to take the square root of that, and that works out quite nicely at 11.2. So we're not at the maximum height there. You know, this has got some speed. But the total energy here, total initial energy, is equal to its total final energy, because the principle of conservation of energy says the total change in potential energy plus the total change in kinetic energy, which is the total change in energy, mechanical energy, is equal to 0. Let's have a look at another problem here. Again, using the same kind of concept. It's just the idea that the energy, the total mechanical energy, is unchanging throughout in a conservative system. So, here we're given an initial height of 10. Notice here the final velocity is 0. That means at the final position there is no kinetic energy. But initially, you know, there is some potential energy because it has some height of 10. There may or may not be kinetic energy. Okay, 1. And that's equal to, well, its speed is 0 here, so all of its energy at position 2 is going to be potential. There will be no kinetic energy. So again, it's just substituting in here. So potential energy, mg times its height here, which is 10, plus its kinetic energy, well, that's a half m times its velocity squared. We don't know what that is, so I'm just going to put in u squared, and that's equal to its potential energy at position 2, which is mg times 32.5. Notice that kinetic energy will be 0 because kinetic energy is dependent on speed. Here speed is 0, kinetic energy is 0. Again, note every single time the masses are all going to cancel. I'm going to double on both sides to give me 20g plus u squared is equal to, I think, 65g. Subtracting 20g from both sides, you can see u squared will have to be equal to 45g, and then just take a square root of that. So u is going to be the square root of 45 times g. I'm going to use my calculator. I'm going to take g to be 9.8, square root of 45 times 9.8, and I'm getting 21 for that one. Square root of 45 times 9.8. Okay, so 21 meters per second. This is something that's launched at 21 meters per second vertically upwards. Okay, and one more example. Well, again, you're solving all these pretty much the same way every time. We know the total energy at position 1 is equal to total energy at position 2 because we're dealing with a projectile. Projectile is an object traveling where the only force acting on it is gravity, and gravity is a conservative force, and in a conservative system there is no change in mechanical energy. The total mechanical energy is unchanging, so the sum of potential and kinetic energy is constant throughout the system. I'm noticing over here in the final row that the final height is 0. So at position 2, there is no potential energy, so all of its energy is going to be kinetic at position 2. Position 1, we have potential energy, mg, times the height, which is what we're looking for, h, plus the kinetic energy, that's going to be half times m, times v squared, and we're given its initial velocity here is going to be 18.5. In fact, let me just write that out. Let me put that in the next line. So there's going to be some kinetic energy and some potential energy here at position 1. So position 1, the potential plus the kinetic energy is going to equal to its total kinetic energy at position 2. The potential energy at position 2 is 0 because the height at position 2 is 0. Potential energy at position 1, that's mg times its height at position 1, which we don't know, plus its kinetic energy at position 1, that's going to be half times m times its initial velocity squared here, which is 18.5 squared, and that's going to equal to its kinetic energy at position 2, which is a half times m times the square of its speed. Now its velocity is negative 30.5, but that means its speed is 30.5. It wouldn't really matter if you put in a negative there, you would still get the same thing. Note the cancellation of the masses. I'm trying to find h. So what I'm going to do is GH will be equal to a half of 30.5 squared. I'm going to subtract a half of 18.5 squared from both sides. So to find h, I put it over here just because space is an issue. H is going to equal to all that stuff on the right side. That's going to be half times 30.5 squared. Maybe I'll factor that out, that half out, minus 18.5 squared, all over little g, whatever that works out as. Again, I'm going to use my calculator for that because that's a little bit beyond my powers of mental arithmetic. 30.5 squared, subtract 18.5 squared, I'll take a half of that, and then divide by 9.8. And that's working out as 30 for me. So its initial height here is 30 meters. Okay, so the principle of conservation of energy, it's written in your formula and tables booklets, I think in this form, that the total change of potential energy plus the total change in kinetic energy is 0. That means the total change in mechanical energy is 0. Mechanical energy is unchanging. That means its total energy at any position is constant. Its total energy remains constant throughout the system if it is conservative. Okay, So practice a few questions on energy, see how you get on.